Assalamualaikum and greetings. My name is Farez Amsyar Zulkifli, and today I will present about my bachelor degree project, which the title is Experimental Study of Milling Process Using Solid Lubricant. First of all, I would like to thank Professor Dr. Liew for supervising me throughout this entire final year. First, the project revolves around the machining of milling process. Milling process is known due to its superior metal removal rate compared to other machining process. Also, it provides a good accuracy and surface finish. Milling process is a conventional process, hence it generates a friction which should affect the machining in a negative effect of energy consumption, temperatures, cutting forces, and machine surface quality, according to Gopala Krishna et al. In 2014. So this is where the lubrication is applied at the contact point of the cutting tool and workpiece, increasing the machining result of the machining accuracy and good surface finish, according to Sloman in 2002. Fast forward, recent technology has seen the use of solid lubricant in industry, especially aerospace industry, which require a very precise and less tolerance of machine product. So solid lubricant usually used as a typical composed of a solid or a binder as an additive powder mixed with base cutting fluid such as oil or water, according to Budd et al. In 2013. On to the next one, which is the problem statement. As mentioned before, friction is a major problem in machining as it causes increase of temperature of cutting tool and the workpiece. The increase on uncontrolled temperature will result in the dimensional inaccuracy of machine surface, poor surface finish, and increase of cutting force. Then the objective of study. First objective is to investigate the effect of cutting speed, feed rate, and cutting conditions on surface roughness and thrust force during the milling of mild steel. And second is to compare the machining performance under dry, minimum quantity lubricant or MQL, and solid lubricant MKL or SLMKL conditions. And then the scope of the study. This study has 4 research scopes, which is material is the first. The material that will be used is the mild steel, the palm oil, and MOX2 powder or molybdenum disulfide. The machine that will be used is a CNC milling machine provided by Faculty of Manufacturing Engineering by University Technical Malaysia Melaka, and the parameter that will be used in this is cutting speed, feed rate, and cutting condition. And lastly, the machining response that will be investigated are surface roughness and thrust force. And now we move to literature review. For literature review, I select 5 previous studies that are related to the title and the parameter of the study. To summarize, study by Zailani et al. In 2011 and Kilicha and Ulutan found that solid lubricant improved the surface roughness and thrust force. And then study by Nalban et al. In 2021, Patru et al. In 2016, and Marquez et al. In 2015 found that MKL conditions improve the surface roughness, tool temperature, and cutting force. The research gap of the study is there is no study on effect of MKL and cutting speed on MOS2 mixed with palm oil. Now we move to the methodology of the study, and this is the flowchart of the study, which the first is lubricant preparation. The lubricant preparation will involve the MOS2 as a particle, S-80 as a surfactant, and palm oil as the base fluid. The S-80 will be used as surfactant to prevent agglomeration and sedimentation. And the particle size is 90 nanometer and the mix concentration of 0.02%. The sonification process will be used lab sonic ultrasonic homogenizer type P series provided by Faculty of Mechanical Engineering by UTM, and the total will be 55 minutes, where the first 10 minutes is only S-80 and palm oil, and the remaining 40 minutes is MOS2 and the mixtures. The amplitude and interval that will be used are 50% and 0.5 respectively. And the cutting tool and workpiece preparation. The dimension of the workpiece is 50 mm in length, 50 mm in height, and 6 mm thickness. And the border cutter and insert are provided by Prof. Dr. Liew and Faculty of Manufacturing Engineering. The grade of the insert are ACM 200 grade. And this is the parameter, the runs provided by the Taguchi. And there is 9 runs, and as you can see, there are 3 levels. The three parameters are cutting speed, feed rate, and cutting condition, and the level of cutting speed are 1000, 1400, and 1800 RPM. And for the feed rate, the first level is 0.05, followed by 0.08 and 0.1 mm per revolution. And as for cutting condition, dry MKL and SL MKL. And this is the experimental condition that I will use in the experiment. And as you can see, the depth of cut is fixed at 0.5 mm, and the flow rate and pressure also are fixed at 150 ml per hour and 8 bar. And for the data collection, the surface roughness will be used the surface roughness tester as an equipment, and where the 10 random reading will be taken as samples to validate data, and the standard deviation will be used at alpha of 0.05 micrometer and UCL and NCL to get the more data without any outlier. And for the thrust force, the dynamometer will be installed and measure the cutting force in real time. And the difference of thrust force or delta Fy will be taken from the start of the highest of one cutting cycle, and the software that we use are the novel software. For the data collection, this is the result of the thrust force. From the table, it could be seen that apart from R4FMKL, SLMKL shows the lowest Fy or thrust force as compared to the other cutting conditions. And for the data collection for surface roughness, same could be said that the SMKL and R9 of MQL show the lowest value of RA or surface roughness. The outcome of this data of surface roughness and thrust force are according to the expected outcome made in PSM I last semester. Then all the data are imported into the Matric software to perform the Taguchi analysis. The analysis will be done by utilizing the signal to noise or SN ratios, and the SN ratios could be interpreted by the highest decibels as the best performance, or the higher the value of SN, the better the process is. And the design that we use is the smaller is better, as we want the surface roughness and thrust force to be as low as possible. And as you can see, the graph shows the positive trend for the increase of cutting speed and cutting conditions against the SN ratio, except for feed rate, as you can see, the value dropped significantly from 0.08 to 0.1 mm per revolution. And this will be further analyzed in the regression analysis. And as stated in the graph, the optimum parameters for producing the lowest thrust force are 1800 RPM of cutting speed, 0.08 mm per revolution for feed rate, and SLMKL of cutting condition. This is the regression analysis done to further study the parameters against the thrust force. And from the analysis of variance or ANOVA, the p-value for all the parameters must be lower than 0.05 to be considered as the significant output. From the ANOVA analysis, as you can see, the feed rate and cutting condition show significant impact to the output, as it provides a lower value than 0.05 except for cutting speed. But cutting speed has a value of 0.054, which means it has 50% of chances to be significant to the output, but still the cutting speed is insignificant to the thrust force response. Then the surface plot is tabulated, and from the surface plot, it proved the past studies by other scholars in literature review and previous SN ratios analysis of cutting speed, where it shows the negative trend of cutting speed against the thrust force. Increase of thrust force from 1000 to 1750 RPM shows a steady decrease of thrust force value, and this could be interpreted as the increase of cutting speed results in a lower thrust force. And the finding is directly opposite to the feed rate parameter, as the graph shows a positive trend of feed rate against the thrust force. Increase of feed rate from 0.05 to 0.1 mm per revolution shows a increase of thrust force. This means that the increase of feed rate results in a higher thrust force. Next, we move to the machining parameters versus the surface roughness. The method of interpreting the SN ratio is similar to the thrust force, and from the graph, as you can see, the cutting speed shows a slight increase of SN ratio value from 1000 to 1400 and a larger increase to 1800 rpm. And for feed rate, 0.1 shows a higher value compared to 0.05 mm per revolution, but slightly lower to the 0.08 mm per revolution. And for cutting condition, SMKL shows a superior SN ratios value compared to dry and also a bit higher than MKL condition. And this could be interpreted as the optimum parameters for the surface roughness are cutting speed of 1800 rpm, feed rate of 0.08 mm per revolution, and cutting condition of SLMKL. And for the regression analysis of surface roughness, it could be seen that cutting speed and cutting collision has a p-value is that way lower than 0.05, and that could be interpreted that cutting speed and cutting conditions show significant impact to the output. This could not be said the same for the feed rate as it has 0.08 p-value, which is higher than 0.05, hence feed rate is an insignificant impact to the surface round output. And from the graph tabulated, both cutting speed and feed rate shows an identical trend of graph which are negative trend against the surface roughness. Increase of both cutting force and feed rate could decrease the surface roughness value. And the result is tally with the past findings by other scholars as mentioned in literature review. And as a conclusion, cutting condition is the most influential parameter in affecting the machine response, followed by feed rate and cutting speed. And increase of cutting speed could produce a better machine surface and lower thrust force. The response are opposite to feed rate for thrust force because higher feed rate results in a better machine surface. And the SLMKL shows the best performance in producing good machine surface and lower thrust force compared to the other conditions such as dry and MKL. And the optimal parameter are 1800 rpm, 0.08 mm per revolution, and SLMKL conditions. And for the, it is recommended to perform the near identical study with this parameter on the harder material as a workpiece to further benchmark the MOS2 particle as a solid lubricant mixed with the palm oil in industry. And that's all for me. Thank you.